Hello everyone. Today I am going to present the determination of environmental micronanoplastics by matrix-assisted laser desorption ionization time of flight mass spectrometry. This paper was published in one of the prestigious journal of analytical chemistry, and it was published recently on September 3, 2020. The contents of my presentations are the introduction. In introduction part, we will study about the literature, the MALDI time of flight mass spectrometer, and the analytes which we will study in this method, and the reagents which used in this process. And next we will study the experiments, results, and discussion. And at the end, we will study about the conclusion of this method. In the current period of human history, it is considered to be the plastic age with the over 335 million tons of plastics that are produced worldwide in 2017. But however, after use, approximately 10% of the plastics ultimately persist in the solid waste stream. These plastic waste degraded and fragmented into the micro-sized plastics and nano-sized plastics. The size of micro-sized plastics are less than 5 millimeter, and that of nano-sized plastics are less than 1 micrometer. The laboratory studies have reported that the ingestion of micro-nanoplastics by organism could cause the biological responses such as the reduction in the feeding activity and depletion of the energy reserves and even mortality of the exposed individuals. So it should be on the top priority to determine or to quantify these pollutants, these micro nanoplastics in environmental and biological samples. Various spectroscopic methods have been used, such as the Fourier transform, infrared spectroscopy, and the Raman spectroscopy. Coupled with the imaging system, the FTIR and micro Raman, such as the micro FTIR and micro Raman, can reach the detection limit to 1 micrometer. But the drawbacks associated with the micro FTIR is in this method we have to identify or to distinguish the particles one by one, which is very time consuming, and the drawback associated with the Raman results, and so that it can be affected by the additives such as the pigments on the micro nanoplastic surfaces. So the matrix-assisted laser desorption ionization time of flight mass spectrometry is a powerful identification technique for the ionization and detection of the intact molecules with high molecular weights. So, this method consists of the three essential components. First one is the ionization, and then the time of flight phase or mass to charge ratio. On the basis of mass to charge ratio, ion separation, and the detection. The polymers were pipetted into the stainless steel sample plate, and then they were vaporized and ionized into the ionization component. Then the charged analytes will be separated under the different voltages and detected by mass spectrometry on the basis of their mass to charge ratio. And this method have the advantages like simple operation, high sensitivity, high throughput analysis, and the reliable results. The nowadays polystyrene and polyethylene terephthalate, or we can call it the PET, is accounting for approximately 90% of the total plastic demand. So, and that have been reported worldwide, occurring in the environment. So therefore the polystyrene and the PET were selected as a representative model in this study to develop the novel approach for the identification and quantification of the micro nanoplastics by application of the MALDI TOF mass spectrometry. The reagents used in this method were the analytes were low mass polystyrene and high mass polystyrene. In low mass PET and high mass PET, their molar masses and their particle sizes are given in the brackets here, and the matrices used are 189 anthracene trivol, and it can be represented as a DIT, and 2,4-hydroxyphenyl azobenzoic acid, which is represented as a HABA, trans 3-indole acrylic acid, which is represented as IAA, and 2,5-dihydroxybenzoic acid is represented as DHB, and cinnamic acid, which is represented as SA. The cationization agents used were the silver trifluoroacetate, sodium trifluoroacetate, and potassium trifluoroacetate, and the solvent used is the tetrahydrofurane. The various experiments were performed, and they were performed in this method. First one is the sample preparation for the MALDI TOF mass spectrometry instrumentation. First of all, the four polymer solutions, matrix and cationization agents were dissolved in THF, and they were then mixed in the tetrahydrofurane, and then for 0.5 microliter sample of this each aliquots was pipetted into a stainless steel sample plate, and then it was crystallized at ambient condition before the spectral acquisition by MALDI TOF mass spectrometry. Thus, according to with a principle with a few millisecond in principle, the mass spectra of the polymer can be obtained. For the quantification study, after the measuring the optimal experimental condition, the quantification process was conducted by the reported method, which is shown here in the reference. For the environmental sample preparation and determination, two environmental samples were adopted for the determination by using the MALDI time of flight mass spectrometry technique. The first one is the aviation plastic cups that is collected from the plastic manufacturing corporation in China, and these cups were then mechanically crushed into the fine powders and liquid nitrogen by a grinder, and then the powder were dissolved in the tetrahydrofurane for further measurement. Another environmental sample is extracted from the sediments. Then the 0.5 microliter of the mixture was measured by the MALDI time of flight mass spectrometry under the optimal conditions. Here are the results and discussion. First of all, the results of optimization of the instrumentation and sample preparation. So the design expert software was used to find the optimal experimental conditions, and the optimized experimental condition for the low mass polymers are the laser energy at 70%, matrix as a DIT, cationization agent as a silver TFA, and make ratio at 24 and ratio 5. Make ratio means the M represent the matrix type, A represent the analyte concentration, and C represent the cationization agent. So on the basis of these three optimized ratio, it was taken as 20:4:5. The high molecular mass polymers optimized ratio was 70%, and the matrix was DIT, and cationization agent was silver TFA, and the MAC ratio was the 20:2:5. The table 1 summarizes the criteria of the response surface analysis for the low mass and high mass polymers. So for both the low mass and high mass polymers, the p-values of the model are lower than the confidence value, which is 0.05. This indicates that the model terms are significant and the results are reliable. At the same time, we can see here the p-values of the lack of fit are above 0.05, so it implies that the lack of fit is not significant relative to the favor error. And the adjusted R-square or the regression values were evaluated as the 0.91 and 0.90 for the low mass and high mass polymers. This which suggests that more than 90% of the response variable results within the scale of the experimental design can be explained by the stimulated model. The optimized condition for the low mass polymer are uh, okay. With optimized condition for the low mass and polymer and the high mass polymers, the identification of the polystyrene and PET micronanoplastics were performed. The mass spectra were obtained for the low mass polystyrene and the low mass polyethylene terephthalate or PET micronanoplastics under the optimized condition, and the peaks appeared here as clearly observed in the figure 1. We can see here the protonated DIT, which is the matrix, and with the addition of the protonated DIT peak, the major series of the equispaced peaks of the polystyrene and the PET polymer were clearly detected. The accurate weight, average molecular weight MW, and the number average molecular weight MN, and the polydispersity index PDI were calculated, and which are here shown as rectangles. The mass difference between every adjacent peaks were consistent with the molecular weight of the polystyrene monomer, that is the 104 Dalton, and the PET monomer 192.0 Dalton. So, and however, due to the existence of the silver adducts, the molecular weights of the protonated polystyrene and PET cyclic oligomers should be 104 multiplied by N plus 108, and the another should be the 192.0 multiplied by N plus 108. The 108 is the molecular weight of silver. The residual masses and of the polystyrene and PET polymers were 58 and 62 Dalton. So therefore the N groups of the polystyrene and the polyethylene terephthalate can be expressed as a C4 H10 and C2 H6 and O2. For the polystyrene polymer, the mass difference is 56 Dalton between the adjacent peaks of the minor and major series, so it indicates that the minor contaminants was caused by the ethylene during the polystyrene production, and similarly, and another figure shows that the mass difference between the adjacent peaks of the minor and major series of the PET was 44 Dalton. So it is in this 44 is equal to the molecular weight of the diethylene glycol unit, and diethylene glycol unit is actually the minor contaminant in the ethylene glycol. These contaminants can be incorporated either within the sequence of the polymer or as in the as in end group. The high molecular weight polystyrene and PET microplastics spectra shows were obtained under the similar optimal conditions for the analysis of the low mass polymers, but with the linear positive mode was used. From the spectra in the figure E and F, the MW, MN, and PDI were calculated, and these are highlighted as red rectangles. The lower PDI values than those of the low mass polymer shows that and the better condensation polymerization of the high mass polystyrene and the high mass PET was occurred. In figure G, further it can be displayed that only one major series of the equispaced peaks was observed in the spectrum of high mass polystyrene, with the expected repeating units difference of the 104 Dalton. The main series of the equispaced peaks with the molecular mass difference of 192 Dalton indicated that the oligomer mass was C4 was C10H8 and O4. A broad peak at the foot of the major peaks to the right side was observed in the figure H, and it might be the peak series of the TFA adduct incorporated into the PET samples. The quantification of polystyrene and PET micronanoplastics was further conducted using the internal standards. When it was plotted as the P normalization versus lone polymer concentration, the result shows that the The data of both polymers fit a logarithmic regression with acceptable coefficient of determination, and the regression value was more than 0.96. So, thus we can say that the reliable quantification results can be obtained by adding the internal standards such as the low mass polystyrene and matrix, and building the relationship between the signal intensity and lone polymer concentration. As we know that the molecular weight of the environmental micronanoplastics are unknown, so both the low mass and high mass polymer measurement should be applied for the sample detection using the positive deflection and linear modes. The mass spectrum for the low mass part of the aviation cup with two matrix peaks represented as A, and five major series of equispaced peaks represented as B, C, D, E, and F, and a few minor series. The peak A were identified as a protonated matrix DIT to the left side, and to the right side it is the adduct or protonated the adduct of DIT to the right side with the molecular weight of 227.0 and 334.0 Dalton. The labeled series B were found with the expected repeating units difference of 104.0 Dalton, which correspond to the molecular weight of the polystyrene monomers. The residual mass of the polystyrene is 58 Dalton after subtracting the mass of the silver adduct, which is 108.0 Dalton. So this can be speculated by the chemical formula of C4H10. The mass difference for the adjacent cluster of the four major series, which is labeled as C, D, E, and F, was 224 Dalton. So it is consistent with the molecular weight of the C16, C16, H16, and O. The mass difference of 14 Dalton between the adjacent peak for each cluster of the four major series can be assigned to the CH2 as a contaminant during the polystyrene synthesization. Here in this figure, the micronanoplastics collected from the sediments of rivers were further applied for the MALDI TOF mass spectrometry analysis. For the low mass part of the micronanoplastics, the peaks can be classified into 6 groups, including the two matrices represented as A, and polystyrene related represented as B, F, and G, and the PET related are represented as H and I, and the other impurity peaks. The peaks label is A, B, and F can be assigned to the protonated matrix DIT and the DIT silver adduct, and C4 H10 silver adduct, and C12 H16 adduct. The another polystyrene related peak series labeled as G was observed with mass difference of 56 Dalton from the peak series B, indicating that the oligomers have the these oligomers have the formula of C4 and H8, and the peaks of H and I are related to the PET, and these can be considered to be the C2H6O2 and with the silver adduct, and C2H6O2 silver adduct. The minor peak series can be also observed, which might be attributed to the residual unknown matter due to the complexity of the environmental samples. Each mass difference of the adjacent peaks and the high mass polystyrene was consistent with the molecular weight of the polystyrene monomer, which is 104 Dalton, but not a certain mass difference was found in the high mass PET part, which can be attributed to the easier weathering of the PET, especially the degradation by some enzymes and fungi. In conclusion, we have studied the novel method was proposed for the determination of environmental micronanoplastics by applying the MALDI TOF mass spectrometry technique, and factors such as the laser energy matrix, enolite, cationization agent, and their ratios were optimized. The polystyrene and PET were identified on the basis of their molecular weights of the corresponding oligomers, and a quantitative correlation was also built with a coefficient above 0.96 for the low mass polymers and 0.98 for the high mass polymers. And future studies coupled with the imaging system, it is greatly anticipated that it would explore the morphology, distribution, and ecotoxicity of the micronanoplastics and the transformation products at the molecular level. Thank you so much.